Hi, this is a mashup of several videos from YouTube that give you an overview of the math in this course. The checkered dots are the complex plane. The x-axis, red, is the real axis. The y-axis is in blue. Time forms a third axis, gold. The yellow is reflecting the fact that the fundamental slowest pattern completes in one cycle, or 2 pi. Here we see a negative cosine wave. Each of these green balls represents a data point in our input data set. The green lines are just to help us see the magnitude. The horizontal gold axis is time. The vertical axis is red, or real. The blue axis has almost disappeared, so we're looking at a 2D plane. Now we're rotating to the imaginary 2D plane. You can see the real has almost disappeared. The imaginary axis is now blue on the vertical. Time is still on the horizontal. And our waveform looks like a perfect sine wave. Now we're starting to see the green lines disappear and more data points being added. Now we're back to looking at our input data, and we see a perfect circle, a perfect sinusoid. This is our data complex plane. This is a summary. Here you can see the blue spiral, and you can see the circle of our data. Now we're going to begin looking at a square wave. The square wave appears as red. It's on the imaginary vertical axis and the horizontal time axis. You can see a square wave is composed of many sinusoids. Each of those sinusoids ends in a blue bar that represents its magnitude. And if we look at it from the right side of the screen, that blue bar pattern is called a discrete Fourier transform, or a DFT. Now we're going to look at input data where there are 3 sinusoids in it. The first is blue, is the largest. The middle is red. The magnitude's much smaller, but it's spinning 3 times faster. The pink is even smaller and is spinning 5 times faster than the original blue, or the original fundamental. When we start taking data, the green dots are going to appear, and you're going to see not a circle anymore, but a completely foreign object. So if you can imagine looking down the golden rod of time into the complex plane, you're not going to see a circle of our data. You're going to see something lumpy. Let's add some more sinusoidal patterns to give it even more twists. So we have this strange pattern emerging. One view it looks like a square wave. This has replaced our circle. Here we're adjusting the number of sinusoids that have been added together to create the square wave. So we're adjusting to 7, and you can see the wiggly pattern in the animation. Let's look at 100, and you can see this shape that looks sort of like some eyeliner that people put on. Adjusting the number of samples so we get a higher resolution, we just see the dots growing closer together. So you might Be saying to yourself, cool, what does a spike look like? What do other shapes in the world look like when we squeeze time out of the spiral? Think of the spiral as a screw. The blue spiral lines are the threads on the screw. The distance between the threads is related to time. The circle with the two blue arrows on it is reality. And we're trying to push that screw through an infinitely thin, two-dimensional sheet of metal representing one dimension of reality. We call these spirals, these screws, winding frequencies, patterns, most accurately sinusoids. So we start with one dimension of reality, the square gold pulse. We fluff it up into a spiral using complex numbers, smash it into the complex domain by removing time, then try to push these screws or sinusoids through reality, measuring how well they fit. There's not just one of these complex planes for all of these sinusoids. Each sinusoid fluffs up reality and creates its own complex plane. Then you try to fit that sinusoid into that complex plane and measure the fit. So we start with our second sinusoid, create a second complex plane, then try to fit our second sinusoid and get another fit value. Now this diagram is for a Fourier transform. We're doing an FFT, so it's a little bit different. It's called a DFT. That's why everything's a little bit different over here. So we repeat this 1,000 or 1,000,000 times, and our goal is to figure out the math. Finally, after we're all done, we've got all these fit values and these sinusoids, and we add them all up, and we should be able to check our work and recreate the golden reality.